Hey there! Here we go, continuing on our rockin' journey of series and an introduction to them at that. In this one, we're going to go over a very important concept known as partial sums. And so partial means part of, sum, obviously adding up lots of stuff. So we're going to go over how to find a partial sum and what it is. And it's very cool to do, and you might be doing a little bit of that or a lot of bit of that, depending on your professor or teacher. It is something you need to know for the BC exam as well. So this says use the sequence of partial sums to find the sum. Ooh, this is how we can actually find the true sum of some series. But most, again, as I said in the very previous video before this, we actually can't find the sum of most series. But the ones we can, sometimes this technique works. So let me show you. Find the first 5 partial sums of the series. So we usually denote a partial sum with S sub and then the number of terms that are in that partial sum. So S sub 1 is going to be equal to just the very first term. So if you were to expand this out, it would be 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3 plus 1/2 to the 4. And that's the first 5 terms in the series. And in the sequence, 1/2 to the n, these are the first 5 terms of that if we were to start at n equals 0. So the first partial sum is quite literally 1/2 to the 0. That's all that it is. It's the first term. The second partial sum means that you take the first 2 terms, and I guess I should write it as S sub 0 and then S sub 1. And that's not to confuse things if we do that, and I'll do S sub 1. You know what? I'll call it S sub 1 as the first partial sum. And then this will be the first 2 terms. Don't be confused that we start at the 0th term. So this would be the first 2 terms, which would be 1 plus 1/2. Right? That's the sum of these first 2 terms. That's all that means. The part of this whole sum that starts with the first 2 terms and ends with the first 2 terms. Right? So 1 plus 1/2 is 3/2. And then the third partial sum, that's going to be the first 3 terms added together. Again, the partial sum. Which partial sum? The third, meaning 1, 2, 3 terms. So we've got 1/2 to the 0 and 1/2 to the 1. We already know equals 3/2. So we take that and we add on the next term, 1/2 squared, which is to the 1/4. When you simplify that with fractions, you'll get 6/4 plus 1/4 is 7/4. Nice. And then the fourth partial sum is going to be equal to the number we got here, because that would be the first 1, 2, 3 terms, which is 7/4. Add on to that the 4th term, which is going to be this term right here. And that's going to be 1/2 cubed, or 1/8. And we simplify that. That's going to be 14/8 plus 1/8 is 15/8. And last but not least is S sub 5, which is equal to the first 4 terms, and then add on the 5th term. So that'd be 15/8. It's the sum of the first 4 terms, plus 1/2 to the 4th is 1/16. This is 30/16 plus 1/16 is 31/16. Okay, so those are the first 5 partial sums. So if you're ever asked for a partial sum, and however many of them, you expand out the series to however many terms that you're asked to. In this case, it's 5. And you add up correspondingly to find those number of partial sums. If you were just asked for the 5th partial sum, that would be it. You wouldn't have to go through all these steps. Okay, now, in terms of use the sequence of partial sums to find the sum, the sequence of partial sums is as follows. It's 1, 3/2, 7/4, 15/8, and 31/16. Now the question is, what is the pattern here? Because these are the partial sums. And if we can eventually figure out what the pattern is of the sums, we call that S sub n, then we have a sequence or an order of these lists, right? Which is great. Because if we then go out to infinity, we can actually figure out what the true sum is. So let's look at this pattern right here. And I'll put that over 1. There's no alternation, but it looks like here we go up by 1. Then we go up by, we go up by 2. Then we go up by 4. Then up by 8. Then up by 16. Looks like we're going up by powers of 2. Right? Because we need to multiply by 2 for every preceding term to get to the next term. So that means that the top is probably 2 to the n. And if I were to add 1 to it, sure enough, 2 to the, that's not going to work. Right? 2 to the 1 won't work. Maybe I need to subtract 1. If I subtract 1, 2 to the first power is 2 minus 1 is 1. 2 to the second power is 4, minus 1 is 3. 2 to the third power is 8, minus 1 is 7. This is the sequence for the numerator of these sums. We'll put that all over. Let's see what's happening here. It looks like we're multiplying by 2 to get to every successive term. So that's repeatedly multiplying by 2. That's 2 to the n. Ooh, but is it? Because 2 to the 1 gives us not 1. And 2 to the 2 doesn't give us 2, it gives us 4. We're off by 1. So if I subtract 1 in the exponent, I'll get 2 to the 1 minus 1 is 1. 2 to the 2 minus 1 is 2. 2 to the 3 minus 1 is 4. And again, remember that each of these terms in the sequence are n equals some number. That's where I'm getting these numbers to plug in. All right, so what we've just figured out is the pattern to the sums. And we know that in a sequence, to figure out what a sequence goes to or converges to, we take the limit as it goes to infinity. So if by chance you're able to get a pattern of the partial sums, we can take the limit as n goes to infinity of them. Now, this is not a trick that works all the time, far from it, but we're going to be able to use it here. So we take the limit as n goes to infinity. Now that actually goes to infinity over infinity, but there is a way to break this down without L'Hopital. We can divide everything as 2 to the n over 2 to the n minus 1, right? And then minus 1 all over 2 to the n minus 1. By doing that, that'll simplify down to the limit as n goes to infinity. 2 to the n over 2 to the n minus 1, you have one less factor of 2 here. So you're going to end up with a 2. You could think of it as 2 times 2 to the n minus 1. And those will divide out. Minus 1 over 2 to the n minus 1. Well, what does this limit go to? As n goes to infinity, this is 1 over infinity. That's going to 0. 1 over infinity, that's going to stay at 2. So we have 2 minus 0, so 2. So all of that work later, and we know that this sum is going to eventually converge to 2. And I'll show you another way of finding that out in another lesson. That'll be awesome. So again, partial sums, sum of the sequence of partial sums, very cool. All right, last but certainly not least, this asks you to find the first 4 partial sums of the series. Ooh. So if we expand this out, that'd be x to the 1 plus x to the 2 plus x to the 3 plus x to the 4. And that is the first 4 terms in the series. And it keeps going on and on and on. We know to x to the n and beyond. That's the pattern that's happening here. This, and we'll talk a lot about these in chapter 10, is known as a power series. It's a series of powers of variables. It's basically an infinitely long polynomial, and it's so awesome. Wait till we get really into the thick of that. Oh my goodness, minds will be blown. Okay, so first 4 partial sums. So the first partial sum, s sub 1, is just x. It's the first term. S sub 2 would be x plus x squared. It'd be the sum of the first 2 terms. S sub 3, the third partial sum, would be the first 3 terms, x plus x squared plus x cubed. No way to simplify that. And then the fourth partial sum would be everything that we've already summed plus that final term right there. And those would be the first 4 partial sums. So if you were asked for the third partial sum, this would be it. But you were asked for all 4 partial sums, so we gave them to you. There we go. That's it. I'll see you in the exercises. Peace.